So we saw our previous part of lecture, we saw a bipartite matching, right, in our paint when we're trying to match people. Here we'll move on to a more general problem of network flow, meaning we have some sort of source, right, and we have some sort of target or sink. Typically source is called S, right, for source, right, and of course you also have a sink or target as T, and then you have some nodes in between. Okay, let me explain what I'm talking about. Again, so new file, right? You have usually, let's call the source, right? And you have a target somewhere here. And you'll have a bunch of nodes in between, right? You may have maybe something like, I'll call them A, B, I don't know, C, and D. Okay, let's put some names onto them, right? Now let's make some, so this will be source, S, right? This is typically called T, right? And these will be, let's call them A. Of course, the names don't really matter here, but, B, C, and D, right? And basically, you are trying to, for now, we're gonna have some connections. Let's add some connections, just basically all connections, right? And these are gonna be basically a directed graph, right? Directed graph. Directed graph. So these will be arrows, something like this, right? All right. These are all the possibilities, right? All the possible. So and you try to, of course, this is kind of it's a very obvious example, but let's imagine for now we have a pass already, right? We have a pass. This represents what's happening already, right? On this way, right? This is so basically we have one connection. It goes S, C, B, T, right? But and of course our task is to see, can we do better, right? Can we do better? Because we want to maximize connections. Why would we want to maximize connections? Because what happens if one connection is cut, right? We want to, want to have a redundancy, for example. Maybe this is some sort of, electricity grid, perhaps. Perhaps this is some sort of, delivery network, some of any sort, right? Many cases, right? So we have this SCBT, and I think everybody here in the class can tell me the solution in this particular case. How could we improve it? How can we do better, right? So we have SCBT, right? SCBT, can we do better, right? So how we better? I mean, it's obvious, right? But you tell me. Well, what would be the solution if without any steps, just give me a solution, right? Can we do better? Well, because remember, so let's imagine this solution does not exist, right? If we cut it off, how would you give me a solution? Like I think the obvious. Yeah, SABT and yeah, you have two. So you have two connections then. So again, you're trying to maximize number of connections between S and T, right? So here it's an obvious, right? SABT and SCBT, right? The problem, of course, arises if you have already. How would this happen in in real life, right? It's a very simple example. If you have here a connection, right? How would we augment this, right? How could we change this, right? How could we make an improvement? So let's see here. If you go to S to C, right? Is there any possibility choice here? This SC is, of course, we look at this pass, right? Is there a possibility? Well, we can't really do anything else here, right? SC, it stays here, right? We have pass, right? But when you go to CB, right? Here we have choice. We see that there's something incoming, AB, right? Possibility, right? So if we make a pass here, right? Then, well, we'll have to make an adjustment, basically, right? So it looks like the way if you have you make this augmentation, basically, right? You need to find a new pass, basically, right? Is there a new pass from SABT, right? So here you can make a pass, right? A replacement, right? If there is one, and then of course you can do also CDT, right? Is there a replacement here? And what can we do to make these replacements? You can use, shortest pass or any pass, basically, or depth first search, basically, right? To check, is there another pass, right? So basic idea is this. If we are here, right, do we have pass from S to B alternative? Yeah, we do, obviously. And then, of course, we can cut this off, right? But we are left with the problem that this is still, we need to find another path, right? So can we find a path from C to T, right? Which doesn't go through these vertices. Of course we can, right? So this means everybody is happy. We have made a replacement by getting rid of this CB, right? Can I do this? Control Z? No, Control Y. So basically I'll use brush, I guess. I'll use this. So we cut this off, right? And we add it here, right? So we add it here, right? Like this obviously, right? And we have a solution basically, right? Again, but we know, again, remember, we now by using depth first search we can find a possibility if there is actually an augmentation, basically augmentation improvement, right? So something like this. Okay, so this is a simple case because we have just connection, yes or no, right? So weights would be what? 1 unit weight. In more general case, if we're going to look at the strongest, like the most universal way of solving this, we could have possibly like weights representing maybe how much stuff can you move, maybe like how much bandwidth, internet bandwidth, network bandwidth you have, right? Or money, gas, anything, right? How much capacity, something called capacity, right? In other words, weight for the graph. So how can we solve this in general case for weighted graph? That's what we're going to be looking at, right? So I'll save this, Control S, come on, Control S, all right, we'll call this maximum flow, right? Add this. Or edge matching, edge pass, edge disjoint pass. Okay, now, so many cases. So let's look at some definitions. I already mentioned there's a source or sink, capacity condition, right? A conservation condition, and value of flow. So let's look at this another example. So again, you have source and on target, right? So right now we have something called capacity for each edge, right? Directed edge. We have capacity. How much stuff can we move? Again, this could be money. It could be, again, I know, network packets. Again, liters of oil, anything, right? So our task is to get as much possible from S to T. Build a network, right? So what's the difficulty here? We have we are allowed partial movement is allowed, right? So we can move 10 or 5, right? So well, it's not immediately obvious what's the most stuff we can move. Okay, first of all, simple. Let's assume this is huge. There's many nodes in between. So what would be the limit? Like, what's the most absolute without knowing much, right? This is a very difficult graph. How much what should be the upper limit? How much stuff can we move? Like, without actually finding a solution, but what would be the limit? Yeah, well, sum of what? Sum of outgoing edges, right? You have 2 edges going out from source. So 30, obviously, 30 is not gonna, you cannot go over 30, right? Or of course you can find also quick and dirty look, also a target. Here you have at most incoming 30. Okay, so it looks like there's a solution of 30, right? Because both sides, source and target, right? Yes. But does it necessarily mean it's going to be 30? Well, not necessarily, right? There could be some problems in between, right? On the way there. But in this case, it looks like I think I can see as a way of getting there, right? You probably can see it too, right? Some solutions, right? So this is a partial solution. So how much stuff are we moving here? We are moving how much? 15 on a SU. Right? So notice there is a conservation condition. If you move in 15 from source to some in between node, like if you're moving oil from from somewhere, or gas from somewhere, over on some pipeline, you cannot leave any drops on a city or a node on the way there, right? You want to get everything. If 15 comes in here, 15 has to leave. Right? That's preservation, right? Conservation condition, right? So it eventually has, has to leave. As much comes in, has to leave, right? I'm talking about the nodes on the way. Now, so this we can see, of course, this is only 20, right? So 15, 15, right? 5 comes here, and we get 20. Okay, so far this left side, I think this left side is, I'll enable editing. Can I draw here? I know I can draw on this, right? Yeah, I think I can. I've been drawing on this one here before, right? Shape fill. Design? No, I don't want design. Insert, some smart art or something, or just home, I guess, right? Painter, I guess there's a way of painting this. Oh yeah. Right, so, oh no, not that. Control C, right? I want just a quick line or something. Oh no, that's not okay. That's not it. All right, now, so you're on the left side. You understand what's happening on the left side, right? Okay. Now we introduce the concept of residual graph. So this is right side. So what is this residual graph? It's like a companion. It's basically a way of visualizing what can we do. So let's look at this. So this is a very powerful concept in this type of network analysis. So let's look at SU, right? We have on the left side, we know 15 is going out, right? So what the residual graph shows, what can be done. Residuals means usually like meaning differences, right? Errors, sometimes use the residuals in statistics, use this as errors, but here it means what can be done, right? So look at this here. How much more can we move from S to U? If you have 15, you can move how much? 5 more, right? And this is the part where the brain might be slightly breaking, right? This part here, this 15, again, sometimes when I saw this like a long time ago, I was like, what's going on here? Why is there an arrow going 15? What this means is that we can adjust, if you're sending 15 units out of 20 from S to U, we can add up to 5 in this direction, but also we can move up to 15 from U to S. And what does it mean moving? Meaning here we can change the flow. We can decrease it by up to 15, right? Because if we're sending 15, right, this graph, this companion graph shows, okay, in this current stage, you can change the flow in the other direction up to 15, right? Meaning we can decrease it, right? So here this represents a decrease, right? That's it, 15 is a max, right? You cannot go below 0, right? Negative flow, right? Because this is a directed arrow, right? So why would you want this type of residual graph maybe? What this type of weird looking graph, right? Well, we're going to be using it to build augmented flows, to build a path, right? Because this type of representation will immediately show where we can find the path, right? So let's see here, right? Obviously here, do you see a way of improving, right? So we use this residual graph to push more stuff from source to target. So basic idea is this. Multiple algorithms exist, but basic idea is, assuming you have this residual graph, which represents the current situation, you find some path from S to T. We know how to find the path, right? Use DFS, depth first search. And let's see, do you see a path here? I see multiple paths actually, right? But, well, do you see here? Well, if I move 5 here, right? What? There's 10. Obviously, if you are moving 5, I cannot use 10 then. I use 5 out of the 10, right? So I use 5, 5. And that's very trivial here, right? Because why? Because I move 5, right? And what happens? I move 5 here, right? And that looks okay, right, to me, right? So we built a path, right? And we have made an improvement, right? Now, but we have some other things we can do. So is that it? Well, I would love to draw it for you guys. Maybe we'll see this here in a moment. I would love to draw it. I know I knew that PowerPoint used to have had you could just draw some random arrows. I guess I'll draw arrows, right? So I guess these are arrows already, right? So I would like to just do some free form drawing. So all right, that's it. Come on, come on. No, all right. So not very good, but basically 5 on. Yeah, so this is 5, 5. Okay, right. So I'll add 5 here, text, right? Not very. Come on, text. T. I thought you could add T. Insert text. So we move 5. So at this situation, this pass is finished, right? Do we have any other pass? Well, we will have, instead of 10, we will have what? We'll have 5 left, right? Okay, and do you see another pass? You probably see. So this pass is what? 5, 5, and 5, right? You have 15, but that's okay. We can take less, right? So 5, 5, 5, right? The only question is now what's going to happen here, right? You see this in the real situation, right? This residual graph, right? It's 15, 15, okay. So what's going to happen, of course, is that we're going to send 5. This means we are going to, the actual effect is going to be that we are going to, if we are increasing 5 here, but the arrow is this way, this means we are going to decrease the flow through here. It's only 10. So only 10 will go through here, and the full out of those 20, right? And 10 goes here, right? So this residual graph will be will be the way of solving this problem, basically, right? By building this graph, because out of this representation, right? It's very hard to see the way of solution, basically, right? So a residual graph is the same situation. It's just a way of representing the possible flows, basically, right? What can you do? And then, well, I wish I had some more, right? Arc or I guess arc, right? So no, that's not it. I guess I don't have really good. All right, so we'll send 5 more, and here, right, it will be mouse. Right, it will be another 5, right? So basically, at the end, I guess I could do it. I guess I should copy everything. Maybe it'll be easier. Or maybe we'll have solutions somewhere here. Maybe I'll see if they have slides. Well, this is going to look more difficult. Oh no, here it will be. Okay, yeah. So, right. So here, right, 10. Right. This is actual situation. And we have how much now? We are sending only 15 at the moment, right? So, right. So here, right, we need to, again, so what's the solution? We build a residual graph, right? And then we find the pass. So let's see if we can, so let's look at this situation. So here, same thing. So let me do this here, right? Right. Let's do a new one. This same solution. So I guess I'll have to draw it myself. That's easier. That's quicker. So S and T, right? And we have in between, I guess we'll call them right. S T T, and this will be what, U and V? Yeah, I guess U and V. Okay, very typical in these problems. More simple. Of course, could be in just a, I don't know, Saulespurens, I don't know, Ugal, I don't know, Ventspils, I don't know, Antalsi or something. I don't know. All right. Okay. So let's draw those arrows. All right. All right. So then, so I'll write this here, right? So we have, right? So if I'm sending 10 here, right? Here we're sending 0 out of 10, right? 0 out of 10. So this means we're sending here 10 out of 30. I mean, it could be out of 500 here, right? 10 out of 30. You'll see this middle pipe is not very that important. It's it's important, but you have bigger capacity, but we're not going to use it. You're never going to use all of it, right? 5, 10, right? So 15, 20, right? So just to check, so on this current stage, how much are we sending from S to T here? How much at the moment? From S to T. Why would you say 10? From 15, right? Because 10 and 5, right? 10 and 5 leaves, and let's check, is it correct? 10, 10, right? It moves, 10 comes into middle, 10 leaves, that's good. Here you have 10 and 15 coming in to V, again, all of the 15 has to leave, right? Otherwise the network would be broken, unless there's somebody stealing, right, stuff, right, in the middle, right? So here, 15, so you see 15, so 15 leaves, 15 enters, all the middle nodes are obeying this conservation principle, right? So again, obviously this is not the final solution, right? To get the final solution, I guess I'll have to open a new paint. Can I do multiple paints here? I don't know. Let's make this smaller. Can you make smaller? Yeah, I can. Okay, good. Right? Let's make a residual graph. Let's make a residual graph. Can I make a new one? Paint. New. No, I guess I can do this? Yeah, I can. Okay, let's do that. All right. So here, again, or maybe I'll copy, Control Z. I'll do this. Yeah. So, I know you love my drawing. Control C. All right. So what we'll do is, in order to solve this, we need to build residual graphs, right? So here on the right side, residual graph. On, let's, where's my eraser, right? So these are we're gonna erase, right? We will need to, right? Oh, look, the awesome eraser, right? Right. So we will need to draw arrows both directions, right? What can be done? So basically, text. What paths are still possible? Basically, answers the question that. Yeah, that's what we are trying to answer. Okay, so let me delete this. Let me erase this. So using the left side, this is the actual state of the world, so to say, right? So we'll have arrows both ways. So in the middle, right? So let's look at the hardest case first, maybe, right? So here, right? Well, how much can we move still? If you have 10 or 20, how much can we still move? 10, right? Easy, right? So again, I'll add 10 again. 10 is okay, right? Also, but of course, how much can we decrease? What's the maximum we can decrease? Also 10, right? So we'll do some arrows. I'll draw again. Let's use this color, right? So, yeah, we can also do 10, right? Let me see how they do the residual graphs, right? Yeah. So in fact, I don't even need this maximum, right? I should just delete this basically, right? This brush, maybe right? So 10, 10. 10 goes, I can increase by 10, I can decrease by 10. How about here? Well, I need, of course, right? Here, well, how much can I decrease? Kind of trick question, but still I'm asking it. This way. Well, can I decrease? Because I'm sending nothing. Can I decrease nothing? No. So this would be 0. Typically, zeros are not written, basically. Typically, these graphs, if you see some examples, right? Let me erase. I need a bigger eraser. How can I make bigger eraser? This is tiny eraser. I need a bigger eraser, right? Right. So we don't need this, right? All right. So we can still send 10. So I'll draw this just here. So 10 and 0, right? How about here? Okay, how much more can we send this direction from U to V? How much more? If you go, again, not looking at anything else, we're driving, we're just looking at the currents from U to V. 20? Yes, of course. Easy. So 20 on this way, how much can we decrease? That's the easy one. How much can we decrease? 10, right? Because we're sending 10, right? So that's the most we can decrease 10. So it's so easy, right? And that's basic, and this solves the problem. So again, here, now, by now you know. So how much more can we send here in this case? How much, what do I have right here? Yes, very good, very good. And back, 15, and that's it. So let's finish this one here. So this one here, this is easy. If it's exactly middle, so you know 5 this way, 5 other way, right? So 5, 5, right? And I think that's why these examples, when I started learning this, is that these even examples sort of don't tell you the full story immediately, because you, okay, it's even, 5, 5, okay, we split in the middle. But the actual idea is that decrease, right? So the arrow the other way represents how much you can decrease the current. So now, using this ugly graph, right, this residual graph, you can find improvements, right? Okay, you can see 5, 5, 5. I see a way of sending 5, 5, 5, right? Also, maybe I can send 5, or let's say 10. Well, I can send 10, 10, and, well, 5 only here. So maybe 5, 5, 5, right? Okay? So yeah, so we use this residual graph. I'll save it, residual graph. Right, to improve, right? So let's look at this part here. This is a tough exercise. You have a source, target, and you have a bunch of these A, B, C. I'll label them. Actually, I'll label them, because otherwise it'll be really hard to do it, right? Right, and I think yeah, A, B, C, D, E, right? F, G, H, I, J. Okay. Now, we have some bunch of stuff. How much are leaving? 1, 2, 5, 6, 12. Right? 12 is leaving. Is 12 entering? Let's double check if everything's correct. Okay, looks okay. Again, looks like 12 is entering, 10 is entering. Okay. But can we do better? Right? Can we increase this flow? It looks already kind of full, right? But can we do better? Are there, so basically, here there's 2 ways of increasing the flow. Let's take a look about this. I see one very easy way. So let's look at the upper part. This is the easy one. Can you find an improvement from this? Can we squeeze in something a little bit more, a tiny bit more, just 1 more unit? Upper part here. Do you see, guys, solution? So, can we send, let's try to push 2 more, right? Not gonna work, but let's try to move, okay? Can we push 2 more here? Okay, now we're stuck, or are we stuck? We're not fully stuck. Well, what can we do? We can move, there's empty space here, right? We can move 1 unit here. We're not dead in water, we can still move 1 here, we can move here, right? So the full pass, so 1 pass would be what? This is the easy one, right? So easy one, I'll do text, right, would be, so we can send, 1 unit from S, A, F, B, G, T, right? From S through A, F, G, B, T onto T, right? So 1 unit. Okay, so that's 1 pass, right? Now the lower case, right? Again, you can see there is, looks like at each step, right, roughly, right? You have these, well, it's not fully saturated, right? How much more could we send here? Do we have room for enough? I think we can do better now, right? So let's look at this here. So this is hard. This is very hard to solve, actually, without a residual graph. If you have a residual graph, it would be very obvious, right? because you have to decrease and increase some flows. I mean, it's not obvious there's a solution at the moment, right? But there is. Can you figure out? Because this will necessarily, it won't be just simple pushing through, it will increase. Okay, we found the first one, right? There's two augmenting paths in this graph. We found the first one, right? I'll give you a hint. You can push 2 units through. So here, speak up, okay.
Can we like push like where there's the zigzag? We can
Yes.
there and then we can.
Yeah. So okay. First of all, the obvious one here is, let's try pushing 2 here, right?
Yeah.
We pushed here, right? 2 more, right? And now we seem to be stuck, right? But that's not everything is lost, because we have this arrow here, right? We can decrease flow here by, obviously we have to do 2. So then we have to do something with this flow here, okay? We push 2 here, right? But since we stuck again, but we are not everything is lost, because we can get rid of this one, decrease flow by 2, and then we have room here, 2, right? So basically, essentially, because this is a learning example, we basically get rid of these 2, basically. We won't need these, right? We just push everything max here, and max here, right? Do you guys see it now? The few of those who are following, right? Right? No. How about everyone else? Because on Thursday we will do this. We'll have an exercise on this, right? So again, the whole thing is to build a residual graph. If we had the residual graph, we basically just find the path, right? We can push through a path and it will be obvious. Here, it's not immediately obvious. I mean, you found it, that's good, but you have a big, difficult graph, right? It's not gonna work as well, right? You won't be able to solve it, right? So here again, maybe we can do one more exercise. We have 2 minutes, or maybe let's look at the algorithm, right? So basically, there's a lemma, right? That you can add. Basically, if there's a path, you can add b units of flow, right? Basically, right? So that's the solution, and there's a proof, and there's the algorithm. 56, Ford Fulkerson, right? So I have a while loop, right? It's super simple algorithm, right? Construct residual graph, and we kind of know how to do this. Find the path with some capacity over 0, and add these b units, and keep doing these residual graphs, right? So basically, you have capacities at most c. So the only question is how complex is this algorithm? Well, that's the problem. You have capacity c. Theoretically, this algorithm could take c iterations. So you have possibly 1,000 units leaving. You have to do it by one, possibly, theoretically, right? You have 5 million units, right? You'll have to check 5 million times, possibly. If you do it slowly, there's some real edge, or we call perverse cases, where this algorithm is not going to be very efficient, right? So that's sort of like the point of this. But I think it's a very simple algorithm, right? We'll implement this on Thursday, right? Now cuts, and we will talk also about cuts on Thursday as well, right? So which is sort of like a companion problem to this. But again, this algorithm, right? So how do we find the path? We have this residual graph, and we just keep going depth first search, right? We keep going, checking whether there is a path, right? From S to T, right? If you find it, great. If you don't find a path, is there no path whatsoever, right? Let's look at this again here, maybe, right? So we have a residual graph. We keep checking. Okay, can we go? We start from S. We do a depth first. Okay, so we go S to U, right? Is there more? Right? We can do here, right? And we are stuck. We can go here, but we have to go here, right? So if there's a path, 5, 5. So that's one iteration, right? If we find max units, we can move through, right? And now let's find another one, right? We can do 5, 5, and 5, right? And then we don't have any more paths. That's it. Right? We try to find more paths. Well, that's it. Right? There's nothing else to do. Because of course this is a very simple example. And in this case, we did not move by one, right? We moved by 5, right? And there are some improvements, this Ford Fulkerson algorithm, which actually make it so you can make a bigger step. So again, so on Thursday we'll do a little exercise on this and try to implement this algorithm in class. All right, so let's see. Yeah, so let's take a break. We'll continue at 11:10. All right, thank you.